Welcome back. This is first of about a lecture and a half on what is known as skip lists. And the motivation behind a skip list is going to be one in which we are able to once again order our elements, which we were not able to do in the previous lecture, which is why we resorted to the heuristics. We'll be able to once again have an order for the elements, a collection of elements that we can put in some order from low to high. And what we're going to want is to have them in a list-like structure. We've already examined the advantages that a list gives us in terms of insertion and removal as opposed to an array. And the problem, though, is that searching can take a while, where if we had a sorted array, we had the advantage of binary search. And just to quickly remind you of what binary search is in case you've forgotten or perhaps haven't seen it, the quick explanation is we're simply dealing with an array of elements and however many there are, and you find the midpoint of the array, the midpoint cell. So we have many, I should draw many cells here to make it clear. Find the midpoint cell, and there's some value there. And you say, well, there's some value x in that middle cell. I'm looking for some other value y. Is y less than x or greater than x? Of course, y happens to be equal to x, then you've found your value. You've taken a guess at one cell, and there's what you're looking for. But if what you're looking for then is less than that value, is not equal to it, but is less than that, then you could recursively search the left side of the array. And if what you're looking for is instead greater than that, you can recursively search the right side of the array. So in this manner then, what we're able to deal with is the idea here that we are able to get away, we can search a sorted array with only log n comparisons rather than n comparisons, because I don't need to start at the beginning and look at each cell. If the array is sorted, I can take advantage of that in the same way I did with a binary search tree, and I could say, well, what we're able to do is to, based on one comparison, determine whether we only need to look at the left side now or that we only need to look at the right side. And that's a big advantage, because then that we've basically eliminated half the cells in one comparison. By comparing to that and realizing what I'm looking for is greater than x, I don't need to look at any of these cells at all. And by comparing to x and realizing what I'm looking for is less than x, I don't need to look at any of these cells. And so that was binary search, for those of you who are not familiar with it. And the search then is log n time, because you're always cutting things in half each time. You have a full array. The next recursive call, you're only searching half the array. The next recursive call, let's say, you look at some value here, x2, and you say, well, y is greater than that, so you only have to search that part. And so now, again, you're down to half the array. And so the idea then becomes that what you are able to do is, at each step of the algorithm, with each one comparison, you trim half the array away until you're, and that's the definition of logarithm then. If you keep cutting something in half until you reach 1, that's the number of times you do that is log base 2. You take 32 and you cut it in half and cut it in half again, you cut it in half again, you're down to 4, and you cut it in half a couple more times, you're down to 1. And that was 5 total cuttings in half, and log base 2 of 32 is 5. And we've gone over that idea before. So the problem is that this doesn't work on a linked list. The array gives you the ability, due to contiguous memory, to be able to say, if I know this is 0 and this is n minus 1, if I know I have n cells, I can quickly jump to cell n over 2 or some other middle area of the cell in constant time. Based on knowing the size of the array, I know where the middle cell can be detected. Where if I have a linked list, I don't have that ability. Each of these nodes is at a different address. And because each of the nodes is at a different address, I don't have the ability to say, well, here's my starting node. This is the head reference, the head pointer. I can't say, well, this is the head pointer, and my list is of size 30, and so therefore I know exactly where that cell is. We can't do that. And so since we don't have the ability to figure out the address of the middle cell from the first and perhaps the last cells like we can for an array, traditional binary search wouldn't work. We can't just jump right off the bat to the middle cell and say, let's compare that. However, what we could do is note that if I had a linked list of some kind, however many nodes it goes to. Actually, I should do this. This is meaning, okay, we got some nodes, and then I'm not going to draw the rest. The point being, I want to be able to say, let's say this happens to be the middle element. So however many elements are in here, and whatever else, let's just say this happens to be the middle element of the list. What if we had some other pointer, in addition to the head pointer, that pointed to that middle node? If I had that kind of a situation, now I do have the ability to jump right to the middle node. I didn't have it inherently in the list, but I've saved some extra pointer to the middle node. Now don't worry for the moment about how would we make sure it's always in the middle or anything like that, because this is not going to be the final answer. But let's just speculate. If we had a list that we weren't doing any insertions or removals into for the moment, then we could say, okay, find the middle element, have a pointer to it, and now, if I wanted to use that binary search strategy, I could. I could say, well, read the middle element, there's some x here. If what I'm searching for is equal to that, then I'm done. If what I'm searching for is not equal to x, but is less than x, then I know this is the list I have to search. But I can stop searching once I hit this node. And likewise, if what I'm searching for is greater than x, then I know this is what I have to search. Pointer next is where I'd start searching. I can skip over all those. Again, assuming a sorted linked list, just like the array had to be sorted. If the list isn't sorted, forget the entire idea. But if it happens to be sorted, if it's an ordered list, then what we have the ability to do is, if we had a pointer to the middle element, we could at least for the first comparison use this kind of binary search tree strategy, or binary search strategy like we would for an array, where I can compare to the middle element and then say, based on how what we're looking for compares to that middle element, search the left or the right half of the list. But we can forget everything else. If I'm looking for something less than x, I can search these but stop when I hit x itself. And if I'm looking for something greater than x, and here's where it really comes in, because if I was looking for something less than x, I could search here, and once I was greater, I could stop. The nice thing we want to be able to do is skip over everything here if we want to search for something greater than x, and that's not something we ordinarily would have had the ability to do. I always have the ability to say, once I reach something greater than what I'm looking for, then stop. So it's not really this part that is really great about this strategy. I'm going to, if I want to search for something less than x, I'm going to search through these, even without this pointer, I would search through these nodes one by one. If the list is sorted, I could stop right there. So I wouldn't have to keep, if I coded a search on a sorted list correctly, I wouldn't need to look at those. But the strength with this idea is going to be that I can jump quickly to the middle and start my search here and not bother with these either. And we didn't have that ability for a sorted list previously. You had to search the entire list from beginning to end, or you could stop early if you found something that was greater than what you were looking for. But now we have the ability to search the first half if our element is in the first half, or we can jump right to the middle and start searching the second half. And that's what we wanted with that array as well. We found the middle cell, and then based on what that middle cell was, we searched the left or the right half. However, the array continued that process recursively, and we're going to want to do that same thing here too. I mean, dividing the list in half with one comparison is really nice, but if then subsequently we need to search the entire list, then that's size n over 2. The search is going to be order n over 2, and that's going to be equal to order n. So it wouldn't, if this is all we had, it wouldn't be any big deal. We would just, okay, we were able to perhaps trim the search a bit, but it's still going to be linear because we end up with a list half the size, and searching that will still be order n time. What we want is, just as the array, we said recursively continue the binary search. Find the middle element, choose the left or right half of the array based on that, and then search that array the same way. So at every comparison, we're trimming away half the array. Likewise, here we'd like to search this list now the same way. We have some other pointer to its midpoint, and say, based on that, I will search the left or the right, or the right or the left portion of that list. and then find whatever small list we're searching, find its midpoint, and then search the right or left portion of it, and so on. But if we're going to make that work, it seems like what we would need is to, given a particular list, have all the midpoints in advance. You know, we have the midpoint of here. We'd also need the midpoint of the first half and the second half, and the midpoint of the, you know, this can be extended now into the situation where we have be extended to the situation where we could say, well, here's the list, and we would need, if this box is sort of where the list was, I'd need a pointer to the midpoint of the list. Then since that lets me search the left or right half, I would need a pointer to both of those midpoints. And based on that comparison, I might search the left or right half of that list or the left or right half of that list. So I need a pointer to each of those midpoints. Based on comparisons, I might search the left or right half of that list, or the left or right half of that list, or the left or right half of that, or the left or right half of that. So I need pointers to the midpoints of those lists. And quickly, it seems like we're going to have a tremendous amount of pointers for this strategy, because every time we look at a list half the size of the one we're looking at now, we say, well, I need to be able to find its midpoint too. So there's a whole bunch of different pointers that we're going to need. And so that suggests to us, well, if I have a whole bunch of different pointers, how do I possibly quickly get the one I want? How do I write this in a general manner to be at all useful? And the answer is going to be, well, let's consider sort of building up from the bottom. Ultimately, if I have only a one-node list, I don't need a pointer to that. It's one node, there's nothing to search. Let's, instead of building it from the top down and saying I need a pointer to the midpoint and a pointer to the midpoint to the two resultant lists and a pointer to the midpoint of each of the four resultant lists, what we're effectively going to end up doing is having a number of pointers to different points in the list. Let's build from the bottom up instead. I have a situation like this, where I have here's the head pointer. We're going to draw 8 nodes. Got to make sure I can fit them all on the paper. Hopefully you can see all those. Looks like you can. And then there's some values corresponding to this. So let's say we have 6 here, and 13, and 26, and 39, 48, 61, 70, and 79. And so the idea then becomes, actually this might make those numbers a little bit visible. I need to write them in a node so you see the structure of things. But that may, if you want to draw this in your notebook, you can probably see those numbers a little easier now. So the nodes we've drawn here are not any different than what we've drawn before. I just arranged them in a different way, and there'll be a reason for this in a moment. But now instead of having the elements like we've done before, where I have the element and then the pointer, I just put the pointer on top and the element on the bottom. It's sort of, taken this sort of list node and rotated it. It's exactly the same list. There's just a reason we're drawing it this way. But each node still contains 2 components, an element and a pointer. So don't get thrown by the new arrangement of the list. What we're going to do then is say, what if we had a list containing every other node? So what if this particular node had 2 pointers, and this particular node had 2 pointers, and this particular node had 2 pointers, and this had 2 pointers? So maybe we have here an array. We start to have an array of pointers. Our head is not just one pointer, it's an array. Where at cell 0, we have the main list. At cell 1, we have a pointer to the second element, which is this whole node. and that contains a pointer to the 4th element, which is this whole node, which contains a pointer to the 6th element, which is this whole node, and that contains a pointer to the 8th element, and that likewise is null. So this list will be only half the size of the previous one, and the reason it's only half the size of the previous one is because we've only got every other node. And so as a result, what this enables us to do is we can search down the list slightly faster because we're skipping a few nodes. And I'm going to very quickly change the battery in the microphone. Okay. So what we have then here is that if I wanted to, I could sort of traverse down the list by way of the second set of pointers, the ones that only go to every other node, and that will give me the ability then to skip down the list slightly faster. Now you might say, well, what if you skip over the value you're looking for? So for example, if I'm looking for 13 or 39 or 61 or 79, this is a great strategy. If I'm looking, however, for 48, I'm going to skip it entirely. And I'd say, well, look, search the top list. You go from the head pointer to 13 to 39 to 61. Oh, 48 must not be in this list, and you'd stop. And you say, wait a minute, 48 was in the list. We just didn't, it wasn't part of that top list. So we didn't want to search it, or we wouldn't find it in our search. And so we don't want to just search based on the top list either, the list containing every second element, because that's not going to cover everything. And yet a search on the bottom list could take a while. So instead, we could, in theory, in fact in practice as well, use this top list to get us close to where we want to be and then drop down to the bottom list for refinement. And that's going to be the key idea to Skiplists as a whole. We're not done drawing the Skiplist picture yet, but the key idea will be that the list right below you is going to have more detail than the list you're on now. And so once you reach the point where you need extra detail, you can drop down to the list below you, but not beforehand. And that's the idea here. What we do is we say, well, I point to 13, this initial pointer at array cell 1. Let me do this. It's clearer that there's a 0 there. So array cell 1 points to the node containing 13. And I say, let's say I'm looking for 48. I say, is 13 greater than what I want? No, it's less. So I know it's safe to jump to this node. Because the list is sorted, if I'm at a node less than 48, it means I haven't passed up 48 yet. Likewise, I can look at this node and say, well, that's 39. I'm at node containing 13 now. My next pointer on this level 1 points to a node containing 39. Is 39 greater than 48? No, it's not. So it's safe to jump from here to here using that pointer because I know I still have not passed up 48. And now I can say the same thing, follow the next level 1 pointer, and I can say go from 39 to this node, which contains 61. So we're saying now, given I have a pointer to this node, if I follow the next pointer to the next node, which contains 61, is that greater than 48? And the answer is yes, it is. So we know that whether 48 is in this list or not, it is not going to be found by looking at level 1 pointers. Because I've got a level 1 node containing 39, and I follow that pointer to 61. So if I want to find 48, and it may well be in this list, and of course you can see it is, but we wouldn't know that yet at this point, it means now it's between the node I'm on now and the next node in the level 1 list. It's between 39 and 61. And since I'm skipping over some nodes, it's possible that 48 is in some node that can be found in a lower list. So at this point, I can drop down and say, instead of looking at the level 1 pointer and finding 61, let me look at the level 0 pointer instead. Let me drop down a level and say, instead of looking at the top list, I already know, given this node, searching the top list takes me too far. Let's drop down to the bottom list and search that instead. And now if I'm on list at level 0, and I follow the level 0 pointer, I reach this node, and lo and behold, we're on 48. We found 48. But I did not need to look at 6 or 26 to find 48. I was able to jump from 13 to 39 I realize 61 is too far, so I drop down to the list below me to refine my level of detail, and that's when I find 48. Likewise, if I had been looking for 26, I could say, well, I jumped to the node containing 13. That's not less than 26, so it's okay to be there. My next node is 39, and that's too big. It's bigger than 26. So instead of following this pointer, I'll drop down a level and follow the level 0 pointer in the node containing 13. And when I reach that next node, that's 26. And this would work for unsuccessful searches as well. If I was looking for 51, I'd say, well, start at level 1. This node is less than 51, so it's okay to jump to here. Follow the level 1 pointer. 39 is less than 51, so it's okay to jump to here. Follow the level 1 pointer. 61 is greater than 51, so it's not okay to jump there. Instead, drop from level 1 to level 0 and follow 39's level 0 list now. And so you look at the next node, and that's 48, which is less than 51, so it's safe to jump to there. And the next node is 61, and that's bigger than 51. And so we know 51 is between 48 and 61. We now need to drop down a level to refine our detail, but there are no more levels to drop. We're on the bottom level. So when you're on the very bottom list, and the node you're on is less than what you're looking for, and the node after you is greater than what you're looking for, at that point it's an unsuccessful search. In situations like being in the list of level 1, you say, okay, if the node I'm on is too small and the next node is too big, it's not a problem because I know there's some nodes in between me that lower level lists have that I don't. The level 1 list does not have 48, but the level 0 one does. So if you're on a higher level list, you can always drop down and say, well, now I've established the range. It's between 39 and 61. Now search that list specifically on the lower level. But once we say, okay, it's between 48 and 61, and so search the next lowest level list, there are no lower levels. This is the list that contains every node, so literally 48 and 61 are consecutive nodes. Unlike in the level 1 list, where 39 and 61 were consecutive nodes. They were consecutive in level 1, but they weren't consecutive overall in level 0. So we could always had the option of dropping down and looking at more detail that we were skipping over before. Now we don't have that option. 48 and 61 are consecutive nodes. We're on this lowest level list. So at that point we know, since we're saying, okay, the rule then is to drop down to the next list and search there, but there's no next list, so we're done. That's the basic idea behind a skip list. We're not done with the picture yet, but that's the idea. That we will have a higher level list consisting of, for the moment, only half the nodes of the list below it. And so I'm able to skip every other node. And I can do the same thing with a level 2. Oops. For here, I will point to every 4th node in the list, not every other node. So this is all one node, this is all one node. And this likewise is null. And what's going on here now is the same thing that went on before, except now the relationship is between the list at level 2 and the list at level 1, instead of the list at level 1 and the list at level 0. What we've managed to do here is to say, I can, if I'm looking for, say, 48, start at the list level 2. And what's the first node in that list? A node containing 39. And that's less than 48, so it's safe to jump directly to this node. Oops. Safe to jump directly to this node. Now I look at the next node in that list, which is 79, following that pointer. 79 is bigger than 48. So I'm at a node that's less than 48. 79 is bigger than 48. I know 48 is between these two nodes if it's in the list at all. And so then I can refine my search by saying, okay, so what I want then is to drop down to level 1 and start searching there. And I say, well, now I know 79 I'm going to hit in 2 nodes, but I know I'll hit 61 in between them. And so when I basically now I'm saying I have this list, 39, 48, 61, 70, 79. That's the span I'm taking into account here. And I'm going to jump to the midpoint, which is 61, by way of saying when I drop to level 1, I will point to the middle of that list, and then the next pointer I know would point to 79 again. So let me check the middle, and I say 61. 61 is greater than 48, so I know it's this range I want to search. And so after that, we've done that already. We drop to level 0, and then we find 48. Likewise, if I was looking for 70, I would say jump to 39. 39 is less than 70, so we can do that. The next node is 79. 79 is greater than 70, so I'm in this range. I drop from level 2 to level 1, and now I say the next level 1 node is 61. Is 61 less than 70? Yes. So I can jump to 61, and then I look at the next node, and of course that's 79, and we know 70 was less than that. So we're searching between 61 and 79. So I drop down to level 0, and now I can search across and find 70. So my path to find 70 was to say jump to 39. That's smaller. We can't jump to 79 because that's bigger. So instead I drop a level to level 1. Look at 61. 61 is smaller. Jump to that node. Look at 79. 79 is bigger, so we don't jump to that node. Instead we drop down one level again, and then we say, okay, now on level 0, the next node is 70, and we found our value. And if we had an unsuccessful search of, say, 72, what we would have done is to say 72, 39 is less than 72, so we can jump there. 79, the next node, is greater than 72, so we don't jump there. Instead, we drop a level to level 1. Now the next node after 39 is 61. Is 61 less than 72? Yes, so it's okay to jump to there. The next node on level 1 after 61 is 79. Is 79 greater than 72? Yeah, we've already established that. So we don't jump there. Instead, we drop down a level, again, to level 0. And now we say the next node after 61 is 70. Is that less than or greater than 72? It's less, so we can jump forward. The next node after that is 79. Is that less than or greater than 72? It's less, or it's greater, so we don't jump forward. And so we drop down a level, and we're on level 0. There's no more levels to drop. We're done. So the basic rule here is whenever you're on a node and you're searching a given level, only one of two things is possible. Given that you're at a node, the next node on that level is greater than what you're looking for, or it's less than what you're looking for. Actually, three things are possible. It could be equal, in which case you found it. But if it's greater than what you're looking for, then the rule would be to drop a level at where you are. If you're at this node, you're looking for something less than 79, you're going to say, this node is too far, drop from level 2 to level 1, and start searching off of that pointer. On the other hand, if we're looking for 82, 79 is not greater than 82. It's safe to jump all the way to here and continue searching from there. So you're always faced with two choices. You're at a node, you're at a particular level that then tells you what pointer to look at that leaves that node. Because if we have, for example, 3 pointers that leave the node containing 39, which one do we follow? Well, if we're on level 2, then we're concerned about the level 2 pointer. If we're on level 1, we're concerned about the level 1 pointer. And if we're on level 0, we're concerned about the level 0 pointer. And so given a node, or a pointer to a node, and a particular level, you look at the pointer leaving that level on this node, and you say the node that pointer points to, is it greater or less than what I'm looking for? If it's greater, then you drop a level at the node you're on now, and if it's less, then you can jump to that node. So you either jump to that node and continue searching, or you say, it's greater than what I'm looking for, so it's too far, so I need to drop a level and refine the detail of the list I'm searching. And that's basically how a skip list is. It's kind of a range check. You're saying, well, I know this is less than what I'm looking for. If this is greater, then I don't jump to that node. Instead, I search between me and this node. And if this is less, then I jump to that node and search between this node and something after it. And that would be the idea. So we might even have one more level on here. This would now be a node containing all 4 pointers for all 4 of these levels, 0, 1, 2, and 3. This would be relevant because, certainly if we've got 8 nodes, you'd ask, why would you want a pointer just to the end? But imagine if we had 15 nodes. So if we had 12 nodes, if we had 12 nodes, for example, we'd want that to be there And then we'd say the 9th node is just going to be 1 pointer, the 10th would be 2, the 11th would be 1, and the 12th would be 3. We continue that this way. So technically, since the list only has 8 nodes, we wouldn't need that there, but our rule here will be, for the moment, we have a list consisting of every node, every 2nd node, every 4th node, every 8th node, every 16th node, every 32nd node, every 64th node. We'll have those kind of lists. And so just to keep that pattern active, we'll say even though that this is the very last node, we'll still have that value there. Because if we had, for example, 12 or 13 nodes, this would become the midpoint then. We will talk a little bit later on about, more realistic variants of the situation. But for now, the way we're going to build things will be a perfect skip list, where you have pointers on every other node, a list containing every other node, a list containing every 4th node, a list containing every 8th node, a list containing every 16th node, and so we'll keep that there. But yeah, if you're asking yourself, it seems like I may be able to get away with things with just having level 2, you're right, we probably could in this case. Or we definitely could in this case. So here, since it's every 8th node, we only have one node in that category. We don't have a node at position 16 or position 24 or position 32, and so there's only one node in the every 8th node list, and it happens to be the ending node in this case. It may be 2nd or 3rd or 4th from the last if we had a few more nodes at the end. So, given this then, the question becomes, how many levels do we expect? And well, clearly what's going on here is that we're going to have what amounts to the idea of saying, I'm cutting the number of nodes in half each time. List 0 has all the nodes. The level 1 list has only half the nodes. The level 2 list has only a quarter of the nodes. The level 3 list would only have 1/8 of the total number of nodes, and so on. So with each increase in level, you're cutting the list in half each time. Eventually, you'd want to get to the point where you just have one node in the list. It'd be like I said here. It seems odd why we'd need that here, but like I said, it's clear if we had 11 or 12 nodes, you'd point to the 8th spot, and then you have 4 nodes after it. So you may still want that top level down to the point of one node in the list, the midpoint, or something around it. And so I'm just going to say order log n. We could get, in this particular list, we could get away with 3 or with 2. But the point is, whether it's log n levels or log n minus 1 levels isn't tremendously important. The point is it's about log n levels. We'll have a level consisting of all the nodes, a level consisting of half the nodes, a level consisting of a quarter of the nodes, a level consisting of the 1/8 of the nodes, a level consisting of the 16th nodes, all the way down to some level at the very top that only has 1 or 2 of the nodes. So it's very quick to search, but what it's basically giving us the ability to do is very quickly check the midpoint or something, potentially close to it. And so as we build this skip list, as we add more elements, then 79 becomes sort of kind of the midpoint of those elements until we have the 16th element added, in which case this would point to there, and we have 2 nodes in that list. And at that point, we might want to add a level 4 to point to element number 16 as well. So we'll basically always have log n levels. And so the issue then becomes, how long does it take to search on this structure? And you may be thinking about insert and remove at this point. Don't worry about it. Just worry about searching for the moment. And the way we'd search in this structure, or the time it takes, we've already basically discussed how, because of the way this is set up, we would always know we wouldn't have to search more than 2 nodes on any list. For example, if I'm searching level 2, I say I'm 39 here. It's 79, let's say I'm looking for 70. Is 79 greater than 70? Yes, it is. So jumping from this node to this node on level 2 would be too long. Would be too long of a jump. We'd pass up what we're looking for. So I jumped down to level 1. But level 1 contained all the nodes in level 2 and then more besides. Level 2, or put another word, level 2 contained half of the nodes level 1 had, every other node. Level 1 contains every other level 0 node. Level 2 contains every other level 1 node. Level 3 contains every other level 2 node, and so on. So I know if these are my 2 level 2 nodes, when I search on level 1, I'll start here, I'll have some node in between, and then I'll end up here. I know I'll do that. I know if I have these 2 nodes, if 39 points to 79 with 1 pointer, then if I drop down to the level below that, I'll get to 79 and 2 pointers. I'll reach the midpoint, and then I'll reach 79. And likewise, I go from 39 to 61 to 79 in 2 traversals. I know if I drop down to level 0, it'll take me 4 traversals. It took me to 1 traversal to get to 61, it now takes 2. You know, leap to this node, a leap to that node. Likewise, starting at 61, it took me one jump forward by a pointer to get to 79. Now it takes me 2. And so total, since I went from 39 to 61 to 79 in 2 pointer jumps, now it's going to take me 4 and the level below that. So we always say the number of nodes in the level below us is twice as many as the current level. And so I know, because of the way this is arranged and the fact that I know I will reach 79 again if I jump from 39 to 79 at level 2 in 1 pointer access, it'll only need me 2 pointer access to get to that same point in the list below me. Because of that, I know I'll never need to look at more than 2 nodes on a given level. I can say here, if I'm at 39, I could jump to 79, and I say, well, no, that's too big. I'm looking for 70, and that 79 takes me too far. I drop down to level 1. I might jump to 61. I do in this case if I'm looking at 70, but I know I probably don't need to bother coding it into the structure. We'll see why in a moment, or we'll see why later on. But I will know if I now look at this pointer after 61, that points to 79. I've looked at 61, I've looked at 79, and 79 is too far. We know it'll be too far. There won't be any way to go past 79 because we kept ourselves from going past it on level 2. There's no way we're going to go past it on level 1. If 79 was greater than 70 when we were on level 2, it's still greater than 70 when we look at level 1. So I know that when I drop from level 2 to level 1, I might have an extra node to look at, but then the next node I might look at, I know the way this all works will be greater than what I'm looking for, and I won't go there. So then the worst that'll happen, I'll either drop on node 61, or I wouldn't have even jumped to node 61 in the first place, and I would drop another level on node 39. Or in other words, we'll spend a constant amount of time on each level. Given any node, we might jump forward 1 node. We will not jump forward 2 nodes. If I was to jump forward 2 nodes, if it was safe to jump from 39 to 61 to 79, then it would have been safe to have jumped from 39 to 79 to begin with on a level higher, and we didn't do that. Since we didn't jump from 39 to 79, we know we're not going to want to make the jump from 61 to 79 later on. So all I'm going to do in the worst case, I'll look at this pointer, jump from 39 to 61, look at that pointer, decide not to jump to 79. A couple pointer reads, a couple comparisons, that's constant time. We're not going to be looking at every node on the level 2 list, or every node in the level 1 list, only a couple nodes. And so we have this many levels. We spend constant time on each level during a find operation. So that's going to be order 1 times order log n equals order log n, worst case for find. And that'll be the structure. If we're looking for some value, we have some x in here that we'd be looking for. We're looking for some value given a perfect skip list, and I can sort of put this in quotes. Given a perfectly arranged skip list where the level 1 is the 2nd, 4th, 6th, 8th, 10th nodes, and level 2 is nodes 4, 8, 12, 16, 20, 24, 32, or 28, 32, and level 3 is 8, 16, 24, 32. When we have a perfectly arranged skip list like we've got here, and you haven't seen the non-perfectly arranged ones yet, so that's why you might not understand what the difference is between perfect and non-perfect. We haven't looked at a non-perfect skip list yet. It'll turn out in reality the non-perfect ones are what we really use, but we're going over sort of the theory first. So we have the idea here of a perfect skip list, and in a perfect skip list, it takes exactly linear or logarithmic time to do a find. We'll spend a constant time on each level, and the end result will be sort of curving downward, where I'd say, if this is my list, level 3, the top level might take me here. I don't want to jump quite so far. Maybe I come here now. And that will sort of be our search path, where I say jump to the middle point, and then the midpoint of that second list, and then its midpoint, and sort of work your way down, progressively refining your level of detail. And so the first jump is very big. And indeed, if I was looking for something greater than 79, I could jump all the way to this node right away. So that first jump could be very big. The second jump won't be quite so big, because now we can say, if I found the midpoint and I'm searching on that, if I know what I'm looking for is greater than the midpoint, now I just search the second half of the list. And so I go from the midpoint of the entire list to the midpoint of the second half, and that isn't quite so much a jump as going from the beginning to the midpoint of the overall list was. Anyway, that's sort of a very small drawn graph. But anyway, that's the kind of search we'll deal with. We'll have a very big leap for our first comparison. The second comparison will be a somewhat smaller leap. The third comparison will be smaller yet, and then smaller and smaller and smaller and smaller as we work our way, forward in the list and down the levels. And that is what we did when we looked for, say, 70. We said, well, 79 is too big, drop a level. I jump all the way to 39, but 79 is too big, drop a level. Jump all the way to 61. 79 is too big, drop a level, jump to 70. Each of these jumps I made was progressively smaller than the one before it, because I'm refining detail. If you're trying to do small refinings of things, you don't want to do huge amounts of work. You don't, if you're trying to, if I had a square I'm trying to color in, I might make large marker strokes to begin with. You may have not seen that. Let me do that again. The paper was too high. I may make large marker strokes to begin with. I'm not going to keep doing that as I approach the edges or run off the edge. Instead, I start making smaller strokes to make sure I'm careful. So I wouldn't go like that and try and fill in. If I go too quickly, I risk running over the edges. So likewise here, the idea would be, it's okay to make quick jumps when we're just kind of searching the upper levels of the list. As soon as we have more limited range, if we're looking for something between 39 and 79, jumping from 39 to 79 is going to take us too far. We instead want to be a little bit more careful and make smaller jumps from 39 to 61. From 61, we don't go to 79. But we say, now I've been able to say, okay, I at least know between this range, I want the second half, I'm looking for 70. And then between 61 and 79, we're able to then refine that even further by saying, now I won't jump all the way to 79, I'll just jump one node and look node by node. But the strength of this is I didn't ever need to read, if I'm looking for 70, 6, 13, or 26, or 48 for that matter. I jumped to 39, then to 61, and then to 70. That's a perfect skip list. The problem comes in that we can't do inserts or removals elegantly at all. Consider, for example, trying to insert 20. 20 should go in that position. However, if 20 goes in that position, what we then need would be a list that looks like this. Here's the old skip list. What I then need is a list that has this viewing to it. Okay, I can at least write that low. We'd have here 6, 13, 20, 26, 39, 48, 61, 70, and 79. There's our level 0. So here's our list of all the values, the level 0 list. And then we'd have some array here. This would be the level 0 pointer. And then I'd have 1 pointing to every other node. And then these would be null. and I'd have level 2 pointing to every 4th node, and have level 3 pointing to every 8th node. So now what I've done is I've inserted 20 into this sequence, and so if you can't read the node values down here, well, they're these numbers with 20 between 13 and 26. The idea, though, is this so you can see on the video everything so it doesn't get cut off. That should do it. A little bit anyway. So the idea here is going to be that now, notice, okay, 6 and 13 could stay the same because they were before 20. But now 20 becomes the single pointer node. So now 26 has to move over and take 39's role as that 3-pointer node. And 48 has to move over and take 61's, or 39 moves over to take 48's role as a single pointer node. 48 moves over to take 61's role as a 2-pointer node. 61 moves over to take 70's role as a 1-pointer node. 70 moves over to take 79's role as a 4-pointer node. And then there's this new node added at the end, in effect, that 79 drops from 4 to 1. Or in other words, what we've done here is a wholesale rearranging the nodes. 26 gained 2 pointers, 39 lost 2 pointers, 48 gained a pointer, 68 lost a pointer, 70 gained 3 pointers, 79 lost 3 pointers. And now it's a perfect skip list still. We have every node, every second node, every 4th node, every 8th node. It's still a perfect skip list, but to go from this top picture to this bottom one, you can imagine would take a tremendous amount of work just to insert 20. So to try and rearrange the numbers of pointers in all these nodes is not really appealing. And in terms of implementation, we don't necessarily need to not have these pointers available. Every single node could have been a node that had all the pointers available to it. We could have an array of pointers if we wanted to. So I'm going to draw a dotted line here. It may have been that we had all these pointers available in the node containing 6. We just didn't use them all. And so in this case, we went from using only one of our 4 pointers to using 3 of the 4 pointers. In this case, we went from using 4 of our 4 pointers to using only 1 of them. So implementation-wise, yeah, we could have an array of the pointers available to start reassigning them. Some of them weren't in use at all. Now suddenly they will be in use. But still, even if we had all the pointers available, instead of having to reallocate nodes, even if we had all the pointers available, and we're simply now deciding to create different pointers now will be used, and some of the pointers that used to be used now aren't being used, that's still going to, just rearranging the pointer assignments is going to take a huge amount of time to go from here to here. So one thing we might do instead is to say, instead of rearranging things, we might take note that we still have the same basic structure of the list. All we've got is this extra node at the end that has only 1 pointer. And the values are different too. So we might say, instead of keeping the nodes having the same values and changing the number of pointers each of these nodes uses, that would be a nightmare of work. Keeping the same values in the same nodes, but changing the pointers around. Let's keep the pointers how they are. Let's say, ignoring the values in the nodes for a moment, here's our old list. What we've done is added a new node to the end that has only 1 pointer. So, here's the structure of our old list. Forget the values in the nodes. Here's the structure. 1 pointer, 2 in use, 1 in use, 3 in use, 1 in use, 2 in use, 1 in use, 4 in use. And now we add a 9th node that has only 1 pointer in use. And then we rearrange the values. That's probably going to be a little easier than rearranging the entire list structure. So don't even worry about analyzing this. That's way too messy. Instead of saying, let's rearrange all the pointers to go from here to here, let's instead say, kind of like we did with the binary search tree, where we said, instead of rearranging the entire list in a tree in a 2-child remove case, what we'll do instead is keep the structure of the tree how it is and rearrange the values. And we can do the same thing here. So that's always a good strategy to keep in mind. Instead of rearranging the entire structure by messing with the pointers, keep the structure how it is, add a new node to the end, and then shift the values down. Or in other words, what we could have done would be this. say that given that I had this list, so if this was my original 13, 26, 39, 48, 61, 70, 79. I'm just drawing a copy of what you see up there now. We're going to when we have room to mess with. A little messier drawing, but at this point you get the idea because it's exactly the same as above it. So here we have our level 0, and then here's our level 1, which points to every other node. And here we have level 2, which points to every 4th node. And here we have level 3, which points to every 8th node. And then these would all be null. What we would do in this case is say, let's add a new node to the end of this. These should continue to be null. Add a new node to the end here. That will be null. And then what I'll do is take 79 and write that here, and I'll take 70 and write that here, and take 61 and write that here, and take 48 and write that here, and 39 and write that there, and 26 and write that there, and then put 20 in there. I don't need to rearrange all the pointers. I can simply add a new node to the end, shift everything over, and stick 20 in. That at least will be linear time, better than rearranging all those pointers. It will be a linear time algorithm, but that's at least better than worse than linear time. We tack this node on the end, shift everything over to make room for 20, kind of like an array, where we'd make sure there's an extra cell at the end of the array, and then move everything over to make room for what we are inserting into the array. We did that when we talked about the array implementation of insert and remove for a list. We said you have to scoot everything over to make room. And the same thing would be the case here, except now we're having the linked list work in a sense the same way, because we want to keep these nodes the way they're laid out. We could sort of shift everything over node by node, and now that we make room there. And likewise, if I wanted to remove a node, if I wanted to remove 20 after that, what I would do is shift all these values over 1, making this node being redundant, and I could get rid of it. So we could do inserts and removes in a perfect skip list in that manner. Insert a new node at the end, shift everything over. When I want to remove, shift everything over to get rid of the removed value. That makes the end node redundant, get rid of that. Each of those would be linear time. So a perfect skip list, we want to keep this perfect structure. We have a worst case of log n for find. We already talked about that. Find or lookup. And then a worst case of linear time for insert and remove. Now, this will be a very fast log n, but log n nonetheless. And so we may ask, well, can we do better than that? And what we'll look at next time in lecture is to say, well, yes, we can do better than that, depending on whether we're willing to rely on the worst or the average case. What we're going to do is take the idea of saying that we don't need to have a perfect skip list. We don't need to have these pointers point to every other node, every 4th node, every 8th node, as long as it's approximate. If 1/8 of the nodes are part of this level 3 list, we don't really need things to be every 8th node. Maybe you can go to node 7 instead of 8, and then maybe go to node 17 instead of 16, and maybe then you jump to node 25 and then 30, and then, if you may sometimes jump 7 nodes, may sometimes jump 9 or 10 to the next node in that list. But the idea will be, as long as about 1/8 of the total nodes are in this list, and those nodes are relatively spread out among the whole list. We don't have everything in the beginning crammed together in that list. Then we expect performance will be cool. But we'll talk about that next time. For now, this is a perfect skip list, and These are the results. What we will look at next time is how we could make insert and remove a little bit faster by relaxing our restriction a little bit. And we'll talk about that next time. See you then.